Hello everyone and welcome back to CSAI TTL. I'm your host and today we are launching into a critical area of algorithmic thinking, navigation the grid. This video is a key installment in our data structure and algorithm series, designed to help you master the spatial logic required for top-tier technical interviews. When we talk about matrices, we aren't just talking about collection of numbers. We're talking about 2D space. As you can see from the spiral traversal on the board, matrices require a different mental map than a standard array. Today, we are going to break down traversal patterns, transformations, and the underlying logic of coordinate system. By the time we are done, these grids won't feel like a maze anymore. They'll feel like a playground. Make sure to follow, like the video, and hit that notification bell so you stay on top of every new topic in the series. Let's jump into the logic. To, mas- to master matrices, you need the right mental model. Stop thinking of them as a math equations and start thinking of them like a building. Imagine you're a mail carrier. The matrix variable is the entire apartment complex. When you write matrix 0, you're stepping into the first floor, the very first row. When you add that second index, like matrix 0, 2, you're knocking on the door of unit 2 on floor 0. Why is this analogy so powerful? Because it makes the index out of bounds error very intuitive. You can't go to the floor 5 if the building only has 4 floors, and you can't look for unit 10 if there are only 3 apartments in a row. In your code, the outer loop moves the elevator between floors, and the inner loop has you walking down the hallway to each unit. If you keep this building model in your head, you'll never get your rows and columns swapped again. Here's a senior engineer warning. Forget your high school math class for a moment. In 10th grade algebra, the y-axis goes up, but in computer memory and grid-based algorithms, we live in a gravity-based system. Look at the diagram on the left. That's the trap. If you try to map XY coordinates from math class directly to the matrix, you'll write buggy code. On the right is the reality of memory. The origin 00 is the top left corner. Moving right is column plus 1, but moving down is row plus 1. Think of it like reading a book. You start at the top and move down the page. In game development, image processing, or pathfinding algorithms, down is always positive. Understanding that gravity pulls the row index down is the first step to avoiding logic errors. This distinction is one of the most aha moments that makes interview problems much easier to visualize. Let's look at the atomic pattern of all matrix work. Row major traversal. This is the standard double for loop. Our code is simple. The outer loop iterates through the floors, which are our rows, and for every floor, the inner loop visits every unit, which are columns. Notice the visual flow. We move horizontally across the first row, then zap back to start of the next row. This is highly efficient for the computer because of the spatial locality. In languages like C++ or Python, the elements of a row are often stored right next to each other in physical RAM. When you process data row by row, the CPU can preload the next unit before you even ask for it. If you were to jump column by column instead, you might slow down the program by forcing the CPU to hunt through different memory blocks. Always ask, am I moving the grain? Am I moving with the grain of the memory? Now let's tackle a legendary interview question, spiral traversal. Most beginners get stuck here because they try to think about when to turn right. This is too complex. The senior way to solve this is to think of it like as peeling an onion. Instead of worrying about turns, we process the matrix in layers. Layer 1 is the outer boundary of the entire grid, which is shown here in the blue color. Layer 2 is the boundary of the smaller grid left inside, red. Layer 3 is the core, the right in the middle. The secret here, the secret inside here is turn right. It's it's not that. It's process a boundary, then shrink the boundary. By defining four walls, top, bottom, left, and right, you can systematically strip away the outer edges until there is nothing left. This layer based approach turns a confusing navigation problem into a clean iterative reduction problem. How do we actually code that onion peeling? We use four steps. We define four pointers: top row, bottom row, left call, and right call. Top row: move from left to right across the current top. Once done, we increment top plus plus because the row is processed now. Right column: move from top to bottom down the right edge, then we write minus minus. For the bottom row, move from right to left across the bottom, then bottom minus minus. And finally, for left call, move from bottom to top of the left edge, then left plus plus. After one full cycle of these four loops, the boundaries have shrunk inwards by 1 unit on all sides. You simply repeat this while your top hasn't passed your bottom and your left hasn't passed your right. It's mechanical, it's predictable, and it's much harder to mess up than manual turn tracking. Even with the four-step method, there is a pinch danger. This is a classic edge case that kills code in production. Imagine a matrix with only one row. Your top loop, or your first loop, processes that row and moves top down. Now top is actually below bottom. If your code doesn't check for this immediately, your third loop, with the bottom row loop, will trigger and try to process the same row again, backwards. This is why we use guard clauses. Between each of the four steps, you should ideally check if your boundaries have crossed. If top greater than bottom or left greater than right, you break immediately. Handling the pinch, where your walls meet and cross, is what distinguishes a robust solution from a lucky one. If you want more practice on these boundary edge cases, explore CSAITTL channel. Diagonal traversal often looks like chaos, but here is a hidden order and a beautiful mathematical invariant you can see use. Look at the indices on the anti-diagonal, the one that going from top right to bottom left. If you look at the cell 02 and its number, 0 plus 2 equals 2. Cell 11, it has 1 plus 1 equals 2 again. Cell 20, 2 plus 0 is 2, finally again. The invariant is this. On any anti-diagonal, the sum of row plus column is constant. This is a massive shortcut. Instead of complex nested logic, you can group elements into buckets based on the sum of their indices. This pattern is essential for problems like zigzag traversal or finding diagonals in a Sudoku board. When you see a diagonal requirement, don't look at the grid, look at the sum of the coordinates. Sometimes a problem requires you to bounce around the grid like a ball in a pinball machine. For this, we use navigation via vectors. Instead of hard coding move right or move down, we define a direction vector like -1 and +1. This tells the code decrease the row and increase the column. The, the algorithm then becomes a simple switch. Add the vector to your current position. If you hit a wall or boundary, flip the switch and swap your vectors to its opposite, like +1 and -1 in our case. This is how snake games or diagonal scan algorithms are written. It decouples the movement logic from the boundary logic, making your code much cleaner and easier to debug. It turns the entire problem into a simple physics simulation. Now let's talk about transformation. Transposition is the main diagonal flip. It's the process of turning rows into columns. Mathematically, matrix ij swaps with matrix ji. But here is the most common pitfall: the double swap. If you iterate through your entire matrix and perform the swap at every cell, you will swap 0, 1 with 1, 0, and then later, when you get to 1, 0, you'll swap it right back. You end up with the exact same matrix you started with. The rule is only iterate the upper triangle, which is the green area. By starting your inner loop at row plus 1, you ensure you only touch each pair once. You flip across the main diagonal, the red slashed line, and stop. This is an ON operation that requires zero extra memory if done in place. Now, how do you rotate an image or a matrix 90-degree clockwise? Many people try to move pixels in circle using complex trigonometry. Don't do that. It's a nightmare to code. A senior trick is decomposition. You break the complex rotation into two simple steps. Transpose the matrix. This flips the dimension. Rows become columns and columns become rows. Reverse each row. This flips the order. If you transpose and then reverse, you get a perfect 90-degree clockwise rotation. If you want counterclockwise, you transpose and then reverse the column instead. By decomposing the rotation into two fundamental, easy to code movements, you eliminate 90% of the potential for bugs. This is a favorite trick for solving rotate image on lead code in record time. Let's visualize that decomposition to prove it works. Look at the number 1 in top left corner of our original grid. After transpose, the row become columns. The 1 is still in the corner, but the 2 and 3 that were next to it are now below it. Notice that the diagonal 159 stayed exactly where it was. After reverse rows, we take that middle grid and flip each horizontal line. The 1 moves from the left side of the top row to the right side of the top row. Look at the final result. The 1 has moved from 0, 0 to 0, 2. It has effectively rotated 90 degrees. This two-step process is not just easier to code, it's also easier to explain to an interviewer. It shows you understand how to break down complex spatial operations into atomic transformations. Before you head into your next technical interview, review the checklist of common pitfalls. Off by 1 errors. Always check if your loop should go to n or n minus 1. A 3 by 3 grid is your best friend. Trace your logic on a small paper grid before you type. The double swap. As we discussed in transposition, ensure your inner loop doesn't restart at 0 and undo your work. Empty input. This is the silent killer. Does your code crashes on matrix equals empty or matrix equals double empty, like in case of 2D matrices? Always add a guard clause at the very top of your function to handle these. Handling these three things successfully is often the difference between a strong hire and a no hire. It shows you consider production ready code, not just the happy path. Let's look at the cost of business. Performance matters. Traversals. Whether spiral or diagonal, you visit every element exactly once. That's a ON time, where N is the total cells, and O1 extra space if you're just printing or summing. Rotation. To do this in place, it is ON square work, because N here is a side length, but the ON space is the gold standard into your look for. Transpose. For a square matrix, it is a ON space. However, for a rectangular matrix, the shape changes. A 2 by 3 becomes a 3 by 2. In this case, you must allocate new memory. You can't fit a 3-unit wide row into a 2-unit wide space. Understanding when you are forced to use extra memory is a sign of engineering maturity. Don't promise open space for rectangular transpose. It's physically impossible. The final takeaway of today's deep dive is don't memorize the code, memorize the movement. Your algorithmic tool belt should be filled with movement patterns, vectors for navigation, layers for spirals, decomposition for rotations, and boundaries for safety. If you focus on the movement, the path the mail carrier takes, and where the walls are, the code will literally write itself. Comment below which matrix topic should we tackle next. Do you want to see the word search with DFS or shortest path in a grid? Your feedback drives our DSA series. Thanks for watching the CSAITTL. Explore our other videos for more DSA and interview prep related content, and I'll see you in the next grid.